and then we can go to the third presenter of today, which is Maria. She's from the Technical University of Crete, and she will present her research, which focuses on advanced optimization methods for industrial scheduling problems. So Maria, the floor is yours.
Hello, everybody.
Maria, at the moment, I don't see the presenter view.
Okay.
Yes.
Okay.
Perfect.
Today I would like to present you a multi-objective Firefly algorithm for the energy-efficient permutation flow subscheduling problem. Now, the permutation flow subscheduling problem is a mathematical model that represents an industrial flow sub environment. Now, in the classic PFSP, we aim to optimize an economical criterion, usually the total completion time of the schedule, known as the make span. Now, due to the rising energy costs and the increase in environmental concerns, the industry shifts towards to more eco-friendly practices. In order to address the modern challenges in industry, we propose an energy efficient version of the classical problem by incorporating both an economical and environmental criteria. We also propose a multi-objective Firefly algorithm for tackling the energy efficient version of this problem, considering three objectives simultaneously. Now, in the PFSP, we have a sequence of machines arranged in a specific order as shown in this figure. We also had a set of jobs that are waiting to be processed on these machines. Now, each machine must be processed exactly once by every machine and in the same order. Now, the goal here is to find the permutation of jobs that minimizes usually the total completion time of the schedule, known as the make span. Now, solving the PFSP can be really challenging, especially when the number of machines is greater than 2. Then it becomes an NP-hard problem. Now, a problem is considered an NP-hard when solving it exactly requires at least non-deterministic polynomial time complexity. So since it's hard to find the exact solution and time consuming, we prefer using approaches like heuristics and meta-heuristics. Now, these approaches don't always guarantee the optimal solution, but they can provide us with efficient solutions within reasonable time. Now, here's an example why the permutation of jobs is crucial for minimizing the make span. In this example, we have 2 machines and 3 jobs, and their processing times are presented in this table. To find an efficient solution, we use a simple yet effective heuristic, the NEH algorithm. The resulting solution is presented in this Gantt chart, which visually shows the schedule and the total completion time, which was estimated in 33 time units. Now here we have 2 schedules side by side, one generated randomly and one generated by the NEH algorithm. Now in the random schedule, we can see noticeable gaps on the second machine. Now these idle periods result to a greater make span compared to the optimal solution provided by the heuristic NEH algorithm. Now, the energy efficient PFSP considers 3 conflicting objectives: the make span, which is the total completion time of the schedule, the total energy consumption, and the peak power. The classic problem is modified to allow machines to operate at different speed level, which represent low speed and high speed. 2 decision variables are considered in this model, the permutation of jobs and the speed level of each machine. Now, we assume that each machine operates at a fixed speed level during the entire schedule. Now, the speed, which is defined as Sj, it's a unitless multiplier of the base rotational speed, which we call RPM1. Now, when Sj equals 1, means that the machine runs at the base rotational speed, while when Sj equals 2, it means that the machine runs double that speed. Now, here we define the make span, which is meaning the time that the last job finishes on the last machine. Now, computing this formulation, we can calculate our first objective, which is the make span. Now, the base processing time is the time when the machine runs at the base speed. The processing time depends on the machine's speed and adjusts accordingly to the second formulation. The total busy time of the machine is defined as the sum of all processing times on that machine at a certain speed, while the total idle time is the difference between the make span and its busy time. Now, the total power consumption consists of two components. As we see here, the power consumption while the machine is processing jobs and the power consumed during the idle times. Now, the base processing power depends on the average processing time, according to the second formulation, and the processing power also increases with the speed of the machine based on a factor of delta, while the idle processing power, it's a fraction of the processing power scaled by a factor of alpha. Now, the energy consumption also consists of two components, the energy while the machine operates jobs and the energy consumed during the idle periods. Now, the processing energy is obtained by multiplying the processing power by its total busy time, and similarly, the idle energy is obtained by multiplying the idle power and its total idle time. Now, the peak power is defined as the maximum total power observed during the entire schedule. Now, here we aim to optimize three conflicting objectives simultaneously: the make span, the total energy, and the peak power. And why is this difficult? So, improving one objective often deteriorates the other one. For instance, if we try to reduce the make span, that causes an increase to the energy consumption as the machines run faster. So, here there is not a single solution. Instead, we obtain a set of optimal trade-off solutions which form the Pareto front. Now, inside the Pareto front, there is not a solution that is better in all the objectives at the same time. Now, the final choice depends on the priorities or the preferences of the decision maker. In order to tackle this problem, we propose a swarm intelligent metaheuristic, the multi-objective Firefly algorithm, which we call MOFA, a randomized net heuristic to generate high-quality initial solution, and a variable neighborhood search and a path relinking to enhance the overall performance of the method. Now, in this figure, we can see the solution framework. Half of the initial population is generated using the randomized net, while the remaining 50% is generated at random. We apply MOFA to the solutions, and we improve the solutions further using the VNS for the first time. Then we apply path relinking, and after that, we further refine these solutions using the VNS one second time. And finally, we apply the randomized path relinking. This process continues for 20 iterations and returns the best non-dominated set of solutions. Now, NEH is a well-known and efficient constructive heuristic, but it produces one solution for a given input. In order to generate multiple initial solutions, we uses a randomized NEH that applies a triangular distribution to select in sensor position. Now, the algorithm starts by computing the total processing time of each job across all the machines and arrange the jobs based on their total processing time in a descending order. Then selects the first two jobs and creates the best sequence for them. In the next step, selects another job from the unscheduled jobs using a triangular distribution. Insert this job in all possible positions in the current sequence and evaluate every possible sequence by computing its make span. and keeps the one with the lowest make span. And this process continues until all jobs are scheduled. Now, MOFA, it's a multi-objective variation of the classical Firefly algorithm. Now, the Firefly is a population-based swarm intelligence algorithm, and it is inspired by the social behavior of fireflies. Now, the fireflies attract to each other through bioluminescence. Each firefly represents a solution, meaning the permutation of jobs and the speed rate of every machine. Now, the machines move toward to the better, non-dominated solutions. Now here's some of pseudocode. The algorithm starts by evaluating each solution based on the three criteria and identifies the Pareto front, keeping the non-dominated solution. Until the maximum number of iterations is reached, for every solution I not in the Pareto front, the algorithm selects a solution J from the Pareto front using crowding distance probability and moves the solution I towards the solution J. In other words, we apply the basic formulations of the classical Firefly algorithm to create a new solution. We evaluate this new solution based on the three criteria, and if the new solution dominates the old one, we accept the new solution. Otherwise, we can accept it, but with a small probability in order to favor exploration. Now we update the Pareto front and we recompute the non-dominated solution. The method repeats itself for 20 iterations and returns the best Pareto front. Now the VNS, it's a method that systematically modifies the way solution changes. It utilizes local search operators like to-op, 3-op, relocate, and exchange moves. We start with a single solution and we set the counter to 0. We choose a random operator from 1 to 6 and we apply this operator to the current solution. Then we evaluate the solution, and if there is a better solution, we update the current best solution and we reset the counter to 0. Otherwise, we discard the solution and we increment the counter by 1. This process continues until the counter reaches its maximum number and the method returns the best solution found. Now, the path relinking is a strategy that explores intermediate solutions between the target and a start solution, and the goal is to discover intermediate better solutions. Here we utilize two versions of the path relinking. In the first version, the target is set as the best solution from the population and the start can be any other solution. We explore the path between the start and the targets, meaning that we try to recompute from the start solution the target solution using one operator. If a better solution is found, then we update the start solution and we repeat until all solutions are explored. Now, the only difference between the two versions is that in the second one, the start and the target solutions are chosen randomly. Now, in order to conduct computational experiments, we use Tyler's benchmark datasets. There are 6 sets of 10 instances each. We run each instance 10 times to obtain the global Pareto front. Now, the global Pareto front consists of 10 individual Pareto fronts that were obtained from the individual runs for each instance. Each set has a different number of machines and jobs, as you can see here in this figure. And this slide presents the global Pareto front obtained for the instance number 11, considering the 3 conflicting objectives, the make span, the total energy, and the peak power. In the 3-dimensional plot are presented the trade-offs between these conflicting objectives. Now, each red point represents a non-dominated solution. We can observe a clear conflict since reducing the make span causes an increase to the total energy and the peak power. The 2-dimensional projections confirm these relationships as the make span and the total energy present a positive correlation and a negative correlation with the peak power. Now, the metric table summarizes the overall performance. The hypervolume indicates an overall good quality Pareto front, while spread indicates a reasonably good distribution of solutions. The total number of solutions in this Pareto front were counted to 47. Here we can see another indicative result for the instance number 26, and we can arrive to the same conclusion as before. The relationship between the objectives seem to be the same. And the impact of the study, I would like to share my views on how my study is relative to the goals of EURECA-PRO. I believe that optimizing the energy consumption and the peak power in the manufacturing systems is a direct contribution to sustainable and resource-efficient production. We propose a novel multi-objective optimization approach to address real-world industrial sustainability challenges. We can also provide a decision-making tool for balances productivity and energy efficiency. And we align with the green transition priorities by reducing environmental footprint in production system. So thank you for your attention. I happily answer if you have any questions.
Thank you very much, Maria, for your clear and informative presentation and for demonstrating how optimizing algorithms can support more energy efficient and sustainable industrial systems. Any questions? I see again a lot of applause. There must be some questions in the audience from your colleague researchers. Yes, Nikolaos.
Hi, thank you, Maria, for the excellent presentation. Thanks all the speakers, actually. I have a question I might not have noticed if you mentioned it or not. I'm assuming that you're using an underlying solver for the optimization problems, which is local, correct? A local optimization solver.
Yes.
Okay, which one are you using and in which environment?
You mean local?
As in not global optimization. You do, so the solution, you mentioned the optimal solutions that you're getting, they're not really optimal, but they're good enough at some point.
Yes, we don't use exact approaches.
Okay, so how do you...
Meta-heuristics and heuristics are methods that approach the optimal solutions.
Okay, okay. And you're applying the entire framework that you presented in Python
In Python, yes.
Okay, thank you very much.
I thank you for your question. If anything else.
We can take it offline as well. I mean, we're in the same institution anyway.
Okay. Thank you so much.
Thank you.
Are there any other questions? I have one, but maybe as I explained before, for me it was really complicated. It's not my topic of research, but I was just wondering, it's really theoretical research now. And have you thought already on how how your approach can be implemented in the real industrial environments? Have you maybe tested this already? Is there also already connection with the industry to apply this theoretical model?
First of all, we need a lot of data in order to be able to provide an efficient solution for their own problem. This is a general mathematical model that may apply to a very simple industrial environment.
Okay.
But it can be more efficient even if it's not directly applied to their own specific industrial environment, even the general form of it.
Okay. Okay, thank you. If I don't see any hands anymore, so that means that there are no... Oh, there's one maybe in the chat. Oh no, it was something technical. Okay, then I would like to thank all of the presenters who presented today their research for the excellent and thought-provoking presentations. And I also would like to thank the audience for being present here today and to listen. And if there are no final questions or comments from the audience, I suggest we end this seminar here today. And on behalf of the EURECA-PRO Doctoral School, I would like to thank also again all of you, and we hope to see you in the next edition of this online PhD seminars, which will probably take place after summer. So there's no edition scheduled before summer anymore, but you will definitely hear from us during and after summer. So thank you all and have a very nice evening. Bye-bye.
Bye.
Thank you. Bye.
Bye.